Let's talk about ARM instruction set architecture in a little bit more detail. ARM is a load store architecture. That means the instructions for accessing memory and for doing computation are different. There is no single instruction that can do both memory access and computation. ARM offers multiple variants of its ISA. Their latest version is ARM v8, which is a 64-bit architecture. A 64-bit architecture means that majority of instructions operate on 64-bit operands. For example, the operands for an add instruction are represented using 64 bits. The earlier version was ARM v7. It was a 32-bit architecture, which means the operands were 32-bit wide for majority of instructions. However, for both ARM v7 and v8, the instructions themselves are represented using 32-bit. So we need 32 bits to encode what operation is to be performed, where the source operands are, and where the result should be put after the computation. There is also thumb architecture, where instruction size is only 16-bit. Having fewer bits to represent instructions reduces code size and memory size requirements. Thumb 2 architecture supports both 16-bit and 32-bit instructions. And in this course, you will use Thumb 2 for your lab exercises. Okay, so an ISA provides registers to hold some temporary values for doing computations. Registers are basically storage location inside the processor. They are very fast to access, and some of these registers are used to hold program variables, and some other registers are used to hold some control state. In Thumb 2, there are 16 general purpose registers named R0 to R15, and there is a status register which is called current program status register. Now all of these registers are 32-bit wide. Each register can hold 32 bits of information. So this is how we represent the registers. So they are 32-bit wide. Bit 0 is the least significant bit and bit 31 is the most significant bit. Now out of these 16 registers, 13 of them from R0 to R12 can be used to hold program variables, whereas R13, 14 and 15 have some special purpose. For example, the register R15, also called PC, is the program counter. It holds the address of the instruction which the processor is currently executing. Link register is used during function calls. It is used to hold the address of the instruction to which the processor should return after executing the function. And stack pointer points to the last used location in a special piece of memory which is called stack. And stack is stack is always organized as last in first out kind of memory. And we will have a detailed look at stack and link registers in coming lectures. The current program status register hold some status flags. The most commonly used four are shown over here. They are negative, zero, carry, and overflow flags. The negative flag shows if the result of a computation that we just did was negative. If it is 1, then the last computation produced a negative result, otherwise it was positive. Same goes for the other flags. For example, 0 flag tells whether the result of the last computation was 0 or a non-zero number. The carry flag tells whether there was a carry out as a result of the previous computation, and the overflow flag tells whether there was an overflow as a result of last computation that was done on the processor. The instruction in Thumb 2 can be categorized in the following categories. The first one is memory access instructions. These are the instructions that transfer data between registers, which are within the processor, and memory. And these are the only instructions that have access to the memory. All other instructions, they can only operate on data which is inside processor registers. They cannot touch the memory addresses. Example of memory access instructions include load register, store register, etc. that you have already seen in the last in few slides ago. The next category is arithmetic and logic instructions. These are the instructions that do some operations. For example, addition, subtraction, shift, logical operations such as AND, OR, XOR, etc. These instructions operate only on registers. They do not have access to the memory. Finally, there are control transfer instructions. During the normal execution, the instructions are executed sequentially one after the other. However, it would be a really boring program if you are just executing all the program right from beginning to the end sequentially. We usually have transfer of control flow inside our programs. For example, if else instructions and maybe switch statements, for while loops, etc. Even function calls and returns represent transfer of control flow. To represent this transfer of control flow during the program execution, there are special instructions in instruction set architecture, and these are called control transfer instructions. For more details about all of these instruction categories, you can have a look at your textbook or Thumb2 manuals. So this is how an ARM instruction looks like. So we said that instructions are either 16-bit or 32-bit. For example, our Thumb2 can have both a mix of 16-bit and 32-bit instructions. Now, the instruction format tells the purpose of each bit inside this instruction encoding. For example, each of these 32-bit means something that helps the processor to decide what to do. Let's look at the most commonly used bits in the instruction format. So here you see opcode from bit 21 to bit 24. These bits tell what is the operation to be performed by this instruction. For example, if all these bits are 0, we want to perform an AND operation. If it's 0, 0, 0 and 1, it's an EOR operation, and likewise. Then to perform this operation, we need some operands. The bits 16 to 19 tell where your first operand is. So this is the number of the register that holds one of the operands. Bits 12 to 15 tell where the destination register is. So after doing the operation, the result should be stored in a register, and these bits tell the number of that register. Now to perform some operation, we might need two operands. One of the operands is here. The second operand is represented by bit 0 to 11. And the second operand might be in different location. It might be encoded in different ways, and how it is exactly encoded is told by bit 25. If bit 25 is 0, that means the second operand is in a register, and which register is represented by bit 0 to bit 3. So this is the second destination register that would be used for the computation. Not only that, the content of this register can be shifted before doing the calculation, and how much they should be shifted is described by bits 4 through 11. If these bits are all 0, then the content of this register will be used as it is for the computation. However, if there is a shift amount, the content of this register will be shifted by that amount, and then the shifted value will be used as operand for doing the operation, which is expressed by the opcode bits. If, however, the value of this 25th bit is 1, then bit 0 till 7 are used as the second operand. So the second operand is not in a register. The value which is here itself represent the operand. So we take this value and use it for computation. Furthermore, the bit 8 to 11 tell us whether this immediate value should be used as it is or it should be rotated before using it in the computation. So the operand 2 can be available in different ways, either in the register and that register can be shifted by some amount, or it can be available as an immediate, and that immediate can be rotated by some amount before doing the computation. So we have already seen the function of bits from 0 to 25. Then the bit 26 and 27 are always 0. They are never used. And bit 28 to 31st represent some condition. The majority of instructions in ARM ISA can be executed conditionally, which means if a particular condition is true, only then you execute that instruction, only then you do that operation, otherwise you don't do anything. And these bits tell which condition should be true for this instruction to execute this instruction. Notice that in ARM Thumb 2, most of the instructions do not use this field. They are always executed.